Okay, this is very much a complete ground-up, sort of almost starting from scratch talk. So I hope I'm not going to bore too many of you. This is aimed primarily at people with small home networks running ordinary wired Ethernet. So, some of what I'm going to say is almost certainly technically wrong, or at least broadly missing out lots of interesting things. But most of those interesting things or details of the wrongness don't generally apply to the kind of networking kit that you're likely to find in your average small home network. So yeah, if I say something that you say, oh, hang on a minute, but you can get to these things which do that. Yes, you might be able to get those things which do that, but generally people won't have them in the home network. Basics of Ethernet networking is, oops, that's interesting. It connects computers together. Used to be that when you connected computers together with Ethernet, they were all effectively on the same piece of cable. That's what was thin Ethernet. These days, almost all Ethernet actually connects stuff together through either hubs or switches. And a hub, sometimes called a concentrator, is just a small device that acts as a center point for the communication. With a hub, if one machine sends a data packet out, the hub will then send that packet to all of the other machines on the network. So it's a broadcast thing. Every machine sees every packet. You can get the problem with hubs is that the packets if two machines try to send at the same time, the packets collide and both packets get lost. So the hubs tend to be less efficient with multiple machines on the same network. So clever people invented a switch, which is basically exactly the same thing, only the switch works out which machine needs to get the packet for its destination. So if PC1 sends a packet destined for PC3, PC2 won't ever see it. So the hubs and the switches basically do exactly the same job. They distribute packets around the network, but the switches are more intelligent and only send the packets where they need to go. So that's sort of the fundamental building block. And I get fed up with this network after a while. Every computer on the network has an IP address. It's not quite true. Every interface on the network has an IP address. Sorry?
At least what?
An interface is basically a network card. One of the things that's not quite true. But, so in this case, each PC has one interface and it's got one connection to the network. And there's some IP addresses just picked entirely out of the air at random. This is what an IP address is. It will be 4 dot separated numbers, each number between 0 and 255. And I couldn't fit in the whole details there, so that's 192.168.0.3 and 0.4. When a computer sends a packet, sends a piece of data, the packet has the source address in it and the destination address. So again, if this machine is sending to that one, the packet that it sends will have in the header from 192.168.0.2 to 192.168.0.4. And if this was a hub and it broadcasts the packet to everything, this PC would receive the packet and say, it's going to .0.4, but I'm .0.3, so I'm just going to ignore that. Drop it on the floor, it's not mine. With the switch is more intelligent and will only send the packet across to this machine. So PC2 doesn't need to ignore it because it'll never see it. There's a little caveat down here. Packets are read only by the destination machine or by a machine in promiscuous mode. You can set a machine up so it says to the switch, yeah, send me everything. Don't care what it is, I just want to see everything. And very occasionally, if you're playing around with network tools, you'll see in your logs interface entered promiscuous mode, interface left promiscuous mode. And it's basically, promiscuous mode is listening to everything that goes on the network. That's more or less all you need to know for setting up a network with a single switch or a single hub and a number of machines. Basically, every machine needs to have a unique IP address, or every interface needs to have a unique IP address, and they will all talk to each other. Where it gets more complicated is internetworking, which is connecting together two networks. So, over that side we've got 192.168.0 something. Over this side we've got 192.168.1 something, with two machines on the network. And the thing that joins two networks together is a router. So a router will have two separate subnets either side of it, or may have multiple subnets. You could have more networks coming off here if you really wanted. And the router moves packets from one network to the other. Notice that the router here has two interfaces, and each interface has its own IP address. So this is where we see the distinction between that a machine can have more than one interface on it, more than one IP address. Right. This is the complicated bit that tends to start where people get confused. Subnet masks. If I just go back to here. Yeah. You'll notice on this side all of the networks are the same 192.168.0. So all the IP addresses. On this side they're all 168.1. And this is where the subnet mask distinction comes in. Right, for example, if you've got an IP address 192.168.0.3 and the net mask, again picking some numbers out of the air here, 255.255.255.0, doesn't appear to make a great deal of sense until, I'm afraid this is the scary bit, you look at everything in binary. And if you convert these numbers to binary, you'll see some random string of noughts and ones, and that one's in the wrong place. But the net mask would always be a string of all ones followed by a string of all zeros. If your net mask doesn't look like that, it's wrong. And basically what the net mask does is it splits the IP address into two parts. The side with all the ones is the network address, or is the network component. And the side with all the zeros is the machine component. And what the net mask does is it splits up the available numbers into a chunk which doesn't change across a network and a chunk which does change across a network. So if we take all of the digits here, where there's a 1 here, you end up with a bunch of zeros at this end and a bunch of data at this end. That number is called the network address. And that specifies the network as a whole. and then every machine on this network will be the same up to this point, and then each individual machine or each individual interface on the network will be different down here. And that's basically what that's all the net mask is. It's a method of splitting up into, this is a network of common machines all talking to each other, and this is the machine identifier on that network. And you may also see this written, because this is all a string of ones, you may just see the number of ones in the net mask written. So you may find that as 192.168.03/24, which is exactly what this is. This is 192.168.03, and then 24 ones in the net mask. That's just a convenient shorthand. Now that with the net masks, notice that we've got a net mask on these IP addresses now. We can talk about what a router does and how a router is set up. So let's take a very simple, it's kind of what you might have in your basic home network. A PC with an IP address that's connected to a router, which has an IP address on this side. It's also been given an IP address on this side, which has been assigned to it by the service provider, ISP, and they deal with everything that's out here onto the internet. Now, faded a bit too much, but never mind. If we look at the setup of this PC, it needs, this is the output of the root command on Linux, ROUTE. This is a very basic routing table. The routing table tells the machine what it needs to do to each packet to get it to the destination. So, the first line is the local network. So it says that everything going to 192.168, and that's a net mask. So everything going to anything on the network specified by these, which is going to be the local network, the 3 PCs that we had up here, has no gateway, so 0000 here means just send it directly, and send it directly on interface Ethernet, which is the main Ethernet interface. So it's basically anything that goes to the local network, send it directly, it'll get there, because it's the local network. And then the second destination is anything going to anywhere else. So in this case, the 0000 means the default route. Local network we can get to just because it's all connected to the same switch. Anything else, which is the internet as a whole, we need to send, the only way we can get to here is by sending it through the router. So in this case, the term gateway here means the address of the router that you send it to. So if this machine wants to send a packet to the local network, it finds that route and says, right, broadcast it on the local network and something will find it. If you want to send something to an external machine, it says, well, it doesn't match that. So we move down to the next line in the table. Oh, it does match that because that's the catch-all. And it's alright, so we need to send all of those packets to that as a first hop, as a first destination. So anything destined for the internet, this machine simply sends it to the router and says, okay, I've been told you know what to do with this. And it's then the router's problem. So we can then look at the configuration of the router. The router also has a routing table. Probably looks very similar. You've got destination, that's the local network. Exactly the same thing on this side. If it's going out to this network, just broadcast it and it'll get there eventually. This side, I'm terribly sorry, there's a mistake, isn't there? This side says if it's going anywhere else, send it to some gateway which is out in the internet here, which the ISP has told you told the router what gateway to use. And that should be one which is this interface. So if the router wants to send a packet to this PC, it broadcasts it. If the router wants to send a packet to the internet, it knows what the upstream is for the internet. And it can send it onto that machine. If the router receives a packet from this machine, which has said, I want to send this to the internet, you know how to do it, go on. So the packet gets to the router. The router then says, well, I've received a packet, it's for some site on the internet, doesn't match that, does match that, and we can send it out on this interface to our upstream gateway. And the upstream gateway then does exactly the same thing, looks at the packet, says, oh, it needs to go out on that connection rather than that connection. And the whole of the internet basically works that way. It just passes packets from one machine to the next, and each machine has its own routing table in it, and each machine will know how to get packets to some subset of specific machines, and eventually there will be a machine that knows how to route that packet to its final destination, and there'll be a machine out there somewhere which will have a direct routing connected to the network that's the destination for the packet. So the routing tables deal with how a computer decides where to send the packet. A couple of words on private networks. You may be familiar with the 192.168 prefix. Many of you, if you've ever had the misfortune to have to delve into your networking, may have discovered that you're using a 192.168 network. Whilst there's something on the order of about 4 billion IP addresses, or IPv4 addresses, that's actually not very many compared to the number of computers attached to the internet, particularly given the way that they allocate these addresses. You can't guarantee to fill every single possible number because they're handed out in blocks and not everybody uses all of the numbers from their block. So IP addresses are actually fairly scarce. And the solution to this is setting up private networking ranges and what's called NAT, which is Network Address Translation. There are three ranges of numbers that you can use for private addresses, private IP addresses. Anybody can use them without any reference to anybody else. And they're special in that those addresses are not routed on the internet. If you try sending a packet to a machine on the internet with the address 192.168.0.4, despite the fact that there are probably many thousands, if not millions, of machines in the world with that IP address, it won't get anywhere. Your ISP will simply drop it on the floor because it's a private address, and because there are many millions of them in the world, it doesn't know which one of them you mean. So they can't possibly send it to the right place, so they don't even bother trying. So you can attach your private network to the public internet, but nobody can send a packet to your machine because it's not routed. Nobody in the internet will send a packet to your machine. However, your ISP has probably given you one single public IP address externally, and they give each one of those to each of their customers. And they'll have a large pool sufficient to deal with their customers. And they'll allocate them randomly to dial-up users. Technically, they'll allocate them randomly to ADSL users as well, or to cable users, but in practice they tend to be quite stable for ADSL and cable. But you can set up the router to do a thing called NAT, where any packet coming from here, where it says, I'm coming from this address, 192.168.0.4, and if you want to send the reply, then send it to that address. Now, of course, if you just left it like that, the packet would get out here, go to its destination. The destination would then say, all right, I need to send a reply to this packet, 192.168.0.1. Oh, you're not meant to bother routing it, are you? So it won't ever get back. NAT fixes this. The router will rewrite the packet coming from here. So the packet comes out with this source address, reaches the router says, I'm NATing, so I'm going to rewrite the source address to my address and keep a record of that packet going out. So it reaches the final destination. The final destination says, right, sending a reply, sends a reply to the router. The reply comes back. The router says, I remember seeing the packet that this one's a reply to, so I need to rewrite it and send it onto this PC. So the outside world only ever sees this one address with NAT. And the router can take any number of machines over here and rewrite the addresses so that it looks like every single machine on this private network, to everybody else in the world, all of those machines are actually look like this one router. So from the internet only sees one machine, and the router fakes it, basically. Makes sure that all of these machines on the private network look like that one machine, so that they're only using one public IP address. And that's why people use NAT. That's what NAT does. Just for the record, those are the private network ranges: 192.168.anything, 172.16. That's a /12, so that's actually split halfway through that number with the if you remember the binary string, and 10.0.8. So 10.anything is a private address range, and you can split these up any way you like. So, for example, my hand system, I use 10.0.1.0 as a /24. So 10.0.1.anything is my main wired network. 10.0.2.anything is my wireless network. 10.0.3.anything is my demilitarized zone where I keep my external web servers and so on. And all of those addresses I NAT onto my my externally visible IP address that my ISP has given me. So any of those machines can reach the internet and get a reply back. Most people will use the 192.168 range as /24s. I'm a bit unusual in using these as /24s, but I started using the 10. Whatever addresses many years ago because they were easy to remember. I can never remember 192.168 when I first started down. A couple of bits of acronym soup. DHCP, which you may have heard of, is a protocol for automatically configuring network things. There'll be a single DHCP server on a network, which, if you're running a home network, will quite often be your ADSL modem or your cable modem. It will automatically hand out to machines on the network that ask an IP address and a net mask. It'll hand out routing details, and it'll hand out information about your DNS server and your DNS search path. And the DNS is the global distributed database that converts names like www.bbc.co.uk to an IP address, which is what computers actually use. It does a few more things than that, but that's basically what it's there for. The DNS is quite important because otherwise you'd be sitting there typing in whatever the IP address is of Google. You'd have to have a list of all the useful IP addresses written down next to your computer. The DNS deals with all of that for you. So that's quite important. The DHCP configuration automatically configures the DNS for you if you're lucky. So both of those, the DNS is vital to have configured correctly. DHCP is a convenience. I'm nearly finished, but a couple of words on troubleshooting, which is a very, very simple sort of step-by-step check of if your network's not working. First thing you do is check that your computer actually knows how to do networking. Ping 127.0.0.1, this is a special IP address. Every TCP/IP network connected computer should have one of these. It's that address, it's called the loopback address, and basically it's for the machine to talk to itself. It makes a lot of things much easier to deal with if the computer can open a connection to itself without having to bother with any funny network drivers. If that doesn't work, you need to check that you've actually got networking on the machine. Make sure that you have TCP/IP compiled into the kernel. Next thing is you ping your own IP address. And that just checks to see whether you've got your Ethernet card drivers working and configured. If that doesn't work, you can use ifconfig, and the ifconfig should give you two stanzas, one for the loopback address and one for this address, and that will have the details of the IP address and the net mask in it. And again, if you don't have at least two stanzas in the output of ifconfig, you need to go back and make sure that you've configured the interface correctly. Next thing is try things on the same subnet, so you're not dealing with any awkward routing at that point. So let's find another machine that you're connected to through a hub or through a switch. Again, if that doesn't work, check both ends to make sure that they've got ifconfig correct and the interface is up and running. Check both machines to make sure they're not firewalling each other. And check to see your hardware. Is the card actually physically working? Is it plugged in? Is it plugged into the right thing? And you can use MII tool or ETH tool, and those will tell you basically, is it plugged into something that, is the cable plugged in? Is it talking at the right speeds? It can give you some basic hardware diagnostics. After that, if you can ping things on the same network, try talking to the router and use the router's IP address. If you can't talk to the router, check the router's actually up and running. Then try a machine on the internet, again by its IP address. You may want to, ahead of time, try and find out the IP address of bbc.co.uk or something, so that you can try that on BBC's web servers. If that doesn't work, you need to check the router's routing correctly, so you should be able to look at the router's routing tables. You need to check your own machine's routing tables, make sure that it's sending, that its default route is aimed at the router. You need to check firewalling on the router. Some routers have firewalls that, if you set that up wrong, could block all the packets. And then the last check is you try connecting to something by name rather than by IP address. And if that doesn't work, check your DNS settings. etc. resolve.conf is usually the file that contains your DNS settings. You don't need to restart anything if you change that file. It's looked at every single time a DNS query is made. And sometimes you'll find that if there's a badly configured DHCP server, it'll override your resolve.conf and you lose all your DNS settings. If you get to the end of that and all of those work and you still can't connect to the site that you wanted to, then the site you wanted to is probably down. So that's the end of the talk. I hope that's been informative. Are there any questions?
If DHCP is given your computer on a network an address, an IP address, how can you ping it if you don't know the address?
It's tricky. You can do broadcast pings. So if you know what the network address is, you can do a broadcast ping to every machine on the network, and then every machine on the network will send a reply back to you. I can demonstrate that afterwards if you want, but yeah, basically it can be quite handy to be able to do a broadcast ping, and then you get a list of IP addresses that you get the response from, and you can say, well, I know what that one is, I know what that one is, I know what that one is. That one must be the one that's missing.
Okay.
So I think that's it.
Thank you.
Thank you.